Hey everyone. Some of this might be repetitive for the people who have come to mental, but I was asked to record something, and I just feel like it's really important to at least get down the basics. So we're gonna go over some things. First things first, quantum mechanics. What is it and what is it used for? Probably supposed to be black, but oh well. So we use quantum mechanics to predict particle behavior, specifically very small particle behavior. Um, This is because when we're in really small spaces, there's phenomena that classical mechanics can't explain. Classical mechanics being like what you did in physics kind of thing. Um, it also explains bonding and molecular interactions. So, so one example that she might have talked about is like the baseball versus the atom. Sorry, if you have a baseball, probably faster if I type it. Oh, versus the atom. You're going to use classical mechanics for the baseball, and you're going to use quantum mechanics for the atom. And other subatomic particles. Cool. And then quantum mechanics itself is understanding that particles and waves are not separate. So a lot of our tiny subatomic particles act as both as a particle and a wave, which is contradictory, but that's what happens when you're really small, apparently. Um, they also tend to have discrete like energy spectrums or quantums. So you have like discrete energy packets that the particle will be able to either absorb or eject. That's a lot of what we get for like fluorescence. And yeah. So then we'll talk about Schrodinger and Eigen. I'm gonna need to write this one. So remember that Schrodinger's equation looks something like this. You have your operator. And I'm sorry, I'm on a laptop, so if it's a little shaky, that's why. You have your wave function. You have your AN, which is kind of like your real value. This is your observable. And then you have your wave function. If you have eigenfunctions, then that means that the wave function is going to come out the same exact function as you put in. So basically, it's going to go to the operator. And I'm going to say core because it might have a multiplier on top of it, and that multiplier will be your eigenvalue. And you only have an eigenvalue if you have an eigenfunction. And your eigenvalue is observable. This is really important because this is like the only thing that you can measure in the lab. This is the only thing that you're going to get any glimpse into what's happening to your atom or particle or electron or whatever. So some examples of that are energy. And I believe momentum is another one, but we'll stick with that one because we'll go into operator. Because our common example is the Hamiltonian operator. Let me try and do an example of this. Maybe one that's not too complicated though. So let's go ahead and delete probability for now. For example, we'll do AX and EAX as our wave functions. And then we'll have our operator as we'll just do derivative. Right, we're gonna have two versions of that. For DAX, I really wish I had brought my tablet. I put it to charge, and then I continued to forget it. But oh well. Also note that the derivative of like an E function is basically gonna be the same. So. So then, right, if you derive that, you're just gonna get A, right? That does not equal your original wave function. Right, because your original wave function was AX over here. So that means it's not an eigenvalue. Sorry, function. Put fx for function. Versus this one, it's the exponent version, right? So we're basically going to get, I believe it's going to be a e to the ax. I want to say that's what's going to give us. Yeah, I'm pretty sure that's correct. But anyway, in this situation, you have, what's the purple? This part right here. This part right here is the same as our wave function. Right? So in which case, this part is equal to our an wave function, where A is going to be our observable. We could have picked a different letter than A, but oh well. So right, in that case, that's our wave function, and then this is our observable. I'm just gonna leave it there. You guys know what observable means. So yeah, so that's two examples of not an eigenfunction, so does not have an eigenvalue. And then this one is an eigenfunction because it comes back the same outside of the thing. And then this is your eigenvalue. I'm just gonna put egg for eigen. You can tell I'm having a bit of trouble writing. Cool. I hope that makes sense. I hope that recorded. So I'm gonna erase it. All right. I don't want to erase it just yet. Okay. Let's also go over probability. I'm gonna need space for that. I guess I'll just leave it up here for now. Note that you're gonna use your probability density function to find your probability. So it's gonna look like the probability density function is just your wave function times your anti-wave function, which in most cases, because we're dealing with real numbers, it's just your wave function squared. And then your probability equation is the integral of that. And you're going to use that for kind of normalization. Actually, no, I think it's the other way around. Yeah, it's your probability. And ideally, because of the thing, you're going to be doing it in absolute value because it's going to be positive. So that's the probability of finding a particle in a certain space. And then your probability density function is the derivative version of that you're going to use for your normalization. I think I was right the first time. You just don't do it squared because it's still the anti. I don't want to erase that. I'm gonna leave myself some space. Okay. Then you're gonna derive that the absolute value version of your density function to get your probability. And it's super similar, which is why I always get a little tripped up. And this still needs the absolute values around it. Oh my gosh. There we go. And that's going to be absolute values of your I really wish I brought my tablet. Go.
All right, we're just coming in really quick.
Okay, no worries. And then if you were to draw your density function, let me put that in text. A function. Let's say energy. Well, 1 to 6? That's a bit high. Let's do maybe 5. And then I'm just gonna go ahead and do 2 lines. We're definitely gonna need more space at this point, so I'm gonna erase these 2. That. And then let's see if we can do dotted lines. Just like that. Cool. So then we'll have our wave function up here. And then we'll have our probability density down here. So because we have an energy level of 5, that means we're gonna have 5 minus 1 nodes. So 5. Four nodes. And the nodes are areas where you have a very low and basically no probability of finding your atom or electron in that space. So your probability in those areas is going to be 0. We'll go ahead and draw our 4 nodes. I like to draw them first, just because it helps with spacing. 2, 3, 4. And then one of the big things about probability is you can't have a negative probability. So it's going to be all positive, right? I'd like to just start here. And you just touch it there. And you go down and not over it, but like just tip it. And ideally, these are all the same height. Yeah. So that's your probability function. And then in the same location where you had your nodes, you also want your nodes for your wave function, right? Because it's those specific energy levels or spaces that you're not going to be finding your atom or whatever. But this time, instead of just being positive, your wave function is going to go up and down over it and go through the nodes. So that's going to be your thing. And this is just 5 minus 1. Those number nodes. Where your nodes are these little, pick a different color. Nodes are these little bits. Where it crosses your little line. And then just a reminder that if you were to have to draw it, your energy at 0, it would be like this. Well, your wave function would be like this. And your probability, then orange, will kind of be more like a bell-shaped curve. So your wave function is, the orange is the probability at 0, energy level is 0. And probably on the exam, you wouldn't have it overlapping like this. I'm just running out of space. And that's at 0. Cool. All right, so I'm gonna go ahead and erase all this now. And then let's see what other practice you guys might need. Let's just practice using the Hamiltonian operator with a very common wave function that she used to give us a lot. So our Hamiltonian in the Schrodinger equation is going to look like this. For that H is your Hamiltonian operator. And then, of course, because Schrodinger equation, you have your wave function is equal to your, in this case, eigenvalue. I believe for Hamiltonian, it's energy. That's your observable. That's what you can measure in the lab. And if you get the same wave function out of the operator as you put in, then you have an eigenvalue because you have an eigenfunction. And then in this case, we'll do our function as square root of 2a. Of course, when you guys are watching the video, you guys are free to speed this up. I know my writing's a little slow. Bear with me, I am on a laptop. Cool. And then our Hamiltonian operator is negative. Your wave function over d. Cool, so right away, we're just going to focus on our derivative part of our operator just because that's the part that's gonna kind of take the most work. I wonder if I can copy and paste stuff. So we're just gonna do the derivative twice because that's what the squares mean. I am definitely gonna see if I can copy and paste this. Let's see if I can do it. We know automatically that that square root of 2a, that's a constant. So that's not really gonna change at all, right? So constant stays out. Let me see if I can copy and paste it. So it stays out. We're dealing with a sine function, so that inner part of the sine function is gonna kind of come out. The n, pi, and a are all constants. The x is not, so the x is gonna be altered. In this case, it's gonna be like the x minus 1 because you're doing derivative, and it's just basically gonna disappear. I'll do that right now. The power of 0, right? Which is just gonna be 1. So we're gonna basically ignore that. And then you have your sine function, which remains untouched because that's one of your that's one of your not log rules, trigonometry rules, I guess. I would say trig rules would be the best description of that. And then we're gonna do it again. We're gonna take our derivative, because it says the d squared. That's not what I mean. I want to talk about that, right? I mean, like up here, it says the d squared and the x squared. And that just means you did the derivative twice. This time you're doing the derivative of your product. So why isn't it letting me copy that? This one's satisfactory. It's actually very annoying. Okay, well. Use the parts. Oh, let me do parts. I guess it's just too much for it. So you know what? I'll just rewrite it. Also remember that because of the x to the power of 0, it's just going to be 0. Sorry, it's just going to be 1. Oh no, it's going to be cosine. This is why copying and pasting is sometimes problematic. Cool. And then that's gonna get us this first part. Those are all constants, they're staying the same. So we'll go ahead and copy and paste that. And then we're doing this part again with the n pi a being constants and the x being like x to the power of 0. So it's basically just going to disappear. And then this time we're going to be negative sign because derivative of trigonometry. So let me leave some space for that. Cool. Then we're going to go ahead and simplify. We're going to get negative n pi a over a squared right? Because it was 2 times, and you're going to just combine that. The negative from the sign came forward. And then guess what? You have the same wave function that you put in. And then you have your wave function, which is wonderful. Because it means that your function was an eigenfunction because you got the same part back out from your operator. Of course, we're not done yet because we had just done this part here. And then so we still have to multiply for the rest of our Hamiltonian operator. That's just gonna go into our eigenfunction, our eigenvalue, sorry. That's just gonna go back into our eigenvalue. So we'll go ahead and do that now. So all this times the rest of our operator. And then I'm not sure how far she wants you to simplify that. I guess probably all the way, huh? I'm running out of room though. Okay. We'll just focus on our eigenfunction. So let me probably rewrite this so that we at least bring our new addition up to the front and it's easier to see. Our new addition being this part of the function. Right, because then that means that this part here, that is such a wonky, is our eigenfunction, sorry, eigenvalue, and then this part here is our eigenfunction. Cool. And then simplifying the eigenvalue, if she does ask for it, is just algebra. I think if you were to simplify it, you would probably get something like h squared n squared over probably 8 ma would be my guess. you want to check that. So cool. There's that one. Let's see what else. I guess I'll start by erasing. I'm gonna go ahead and pause share while I do that. Okay, cool. So I've erased it, and I've also got us a new operator. I believe this one's the momentum operator. It does, however, start with a d over dx, so I just kept the original derivative that we had done in the last problem, just to save some time. So that's this part here. And then from there, our product is just going to be multiplied by negative IH. Anyway, as I was saying, we're using the momentum operator on the same equation, just so you guys can see that different operators will treat the equation differently. So as you can see, this one only had one derivation, and we ended up with the cosine version, which means that you in fact did not get the same wave function out of the operator. So you do not have an eigenfunction. You don't. So you can assume that you have an eigenvalue. However, you are able to find the expectation value by normalizing your function. And what an expectation value is, it's just the average of basically all the little would-be eigenvalues of your equation. And the way you do that is you plug it into a very long equation. An equation looks like this. I'm gonna pause recording while I write it. Okay, so this is your expectation value equation. You should probably already have this on your equation sheet somewhere. But from here, you're just going to plug in your wave function, your original one, not the one with the operator. I'm going to go ahead and copy and paste because that's going to be a lot of writing. I can. Right. Because we're dealing with real values, and she should never ask you to deal with a wave function that has, especially not for something this big, she shouldn't be asking for complex numbers. If she is, then she's either warned you ahead of time or she's just being weird. So that's just that device. And then you're gonna have your A operator here, which in this case should probably be the same operator that you used. You're just gonna leave it as is. You can just write A there. She usually doesn't have you solve for expectation value. Just because it can be such a big equation and it will take a long time on the exam. You want to be nice, you can sort of condense and simplify it, but other than that, you can just leave it as is. And yeah, that's about it for today's session. Thank you guys for coming or for listening. Bye.